I'm starting the record, um, and I'm going to share my screen. We're looking at 4.1 just in case you need to make a note. And I do encourage you to make notes as we go through. But 4.1 is all about inverse variation. So here we have the inverse variation. Can y'all see my screen? Can you see what I'm pointing at? Okay, great. So inverse variation is a specific type of relationship. And that's one of the most important things that I want you to take away from what is an inverse variation. It is a relationship between two variables. So it's a relationship between two variables. And what is that relationship? So that relationship says that as one variable goes up, the other variable must go down. And one of the important pieces is how does it go down? It goes down what we call proportionately. So it goes down proportionately. What in the world does that mean? So that means that, and we'll look at it in this example, that means that as x goes up, then y goes down. And to check to see how it goes down and to make sure that it does go down proportionally, then you can look and see, you can test it by the product of the two variables when you multiply them together. So when you multiply them together, and we can look at that using this last row on the example. We're going to multiply x and y together, and the result anytime we multiply is the product. Y'all agree? Thumbs up. Yeah. So 1 times 12 is 12. 2 times 6,
12,
12. 3 times 4,
12,
4 times 3,
12,
6 times 2,
12,
and 12 times 1.
12.
Still 12. And so what we notice is that the product, when you multiply the two variables together, is constant. It does not change. 12, 12, 12, 12, 12, 12, over and over and over. That is our test. That's what we check for to see if it's an inverse variation. And so if the product does not change, then yes, it is an inverse variation. So that's very important, very important, very important. Are we good? So example 1 asks us to look at some other problems and see if they actually are inverse variations. And if I share this screen, navigating back and forth is not always the easiest thing in the world. So now do you see the Pearson screen? Okay, so if I share this screen, then what you're going to see is they're asking you, and this is one of your try-its. So this would be an easy way to check it out. Does this table represent an inverse variation? Well, what did we say? How we were going to check for that? What is our test? We're going to test it by multiplying the two variables together. So if we look at the 1 times 20, what do we get? 20. 2 times 17 is
34.
34. Yeah. 3 times 4.
42.
So is our product, I mean, we really don't even have to go any further than that. Is our product constant?
No.
No.
Nope.
So it's not an inverse variation. Very easy, just simple check. If you have a chart, then you can just calculate your product for your chart. So now let's look at example 2. Example 2 says, and this is where it can get a little on the tricky side, but it's still easy. You just have to know the pieces. So what's very important is this formula right here. So we're looking at rational functions. Remember back to Algebra 1, and don't cringe on me. I know that y'all have some nasty feedback sometimes about Algebra 1, but what is a ratio? Is the whole number 1 a ratio?
Fraction, ain't it?
Yeah, that's exactly right, Jonathan. A ratio is a fraction. And so k divided by x, that's a ratio. And that's what we're looking at is, you know, from that base word ratio, we're looking at rational functions. So rational functions. When we look at rational functions and we graph them, you're going to see something on the graph. In fact, I have a graph pulled up, and this is of what we call the parent function. So remember, the parent function for quadratics is simply f of x is equal to x squared. You know, it's the most simple form of a parent function. So that's for quadratics. But now we're looking at rational functions. And so the parent function for a rational function is simply 1 over x. That's the most simple function of a rational function. And so if I show you the Desmos, when you're graphing a parent function, look at Desmos and what do you see? I mean, what's something that really jumps out at you?
They're opposite.
They're opposite. Do they ever cross the origin?
No.
What's one thing we know about having a 0 in the denominator of a fraction? Can it happen?
No.
No, it cannot happen. And so if we're thinking about domain and range, whew, Ms. Harrison's really pulling out some of these terms from Algebra 1, right? Think about domain and range. What is domain? All right, I can see a coloring sheet coming y'all's way. So I'm going to go back and swap the screen share with you again. So let's look at domain. Domain is simply all the x values. So any value that x can be is your domain. If domain is all of your x values, what do you think range is?
All your y values.
Yep, all the y values. And so if our parent function for a rational function is 1 over x, and we saw that Desmos graph that basically it approached the origin, but it never touched the origin. That is the example of an asymptote. And that's one of your vocabulary words for this week is asymptote. So it's basically where the graph does not exist. Where does it approach, but it can never equal. And so if we were looking at domain for this parent function, then we know that x can never equal 0 because otherwise the function does not exist. And we see that in our Desmos graph. X never equals 0. If we're looking at the range, then the range, it never touches the 0 because there's never a place where 0 is equal to 1 over x. And remember that the other word for we use for y values is f of x values. And so 0, this fraction can never equal 0. And so that's why the graph looks like it does. It approaches 0 and it is opposite. And so we would call this, do y'all remember how we denote range? So it would be negative to infinity to negative infinity, and it approaches 0, and then positive infinity, 0 to positive infinity, but it never equals 0. So we would say domain does not equal 0, like that. This is not as important. I'm just, talking to you about the graphs. When we get into 4.2, that's when we're really going to start looking at the graph portion of it. Are there any questions up to this point? All right. So this is information. Now let's go back to testing for rational functions. Jonathan, how you doing?
Pretty good.
All right. So we have this example that says, in an inverse variation. So that tells us automatically that we have an inverse variation. So in an inverse variation where x is equal to 10 and y is equal to 3, write an equation to represent the inverse variation. And then it asks us to find the value of y when x is equal to a negative 6. So they've already told us that this is an inverse variation. So here's our formula that we need. So if we have an inverse variation, the formula is y is equal to k, which stands for some constant. In the parent function, what was the constant? Look at this formula. We talked about the parent function, which is the most simple version of it. What was the constant? What's k in the parent function? Mm-hmm. 1, because it's whatever that value is in the numerator of the ratio. So it's simply 1. What if we had y is equal to 2 over x? What is the constant? 2. Yeah. So here we have a y value and we have an x value right here. And we're simply going to plug it in to our formula here to solve, because we need to know what k is. To be able to write the equation, we need to know what k is. And so what did they say our y was? So 3 is equal to k, which we don't know, we're going to solve. And what is our x? 10. And so how would we solve for k from this point?
Multiply 3 and 10.
Yeah. Multiply. And so 30 is equal to our k. So to write our equation, it is simply y, because that's a variable. 30 is our k over x. That's all we have to do. And so once we have the equation of the rational function, then we can calculate all the different variables, because remember, this equation just shows us exactly what it looks like on the graph. So as x changes, your y changes, because all of your coordinates are going to change. Good, it's just simply a function. So now let's look. They asked us, what is the y value? What is y when x is equal to a negative 6? So here we have y is equal to 30 divided by negative 6. So y is equal to what?
-5.
Yeah, negative 5. And why did you say negative 5?
Because there's a negative.
Because this is a positive 30. When you divide a positive by a negative, the answer has to be a negative. And so that simply says that when x is 6, y equals negative 5. When x is 6, y equals negative 5. And so let's look and just confirm that on our Desmos. So we have y equals, and what was our formula? What was our constant that we solved for to start with? What was our constant? Show me again, Brooke. I was looking at, yeah, 30. Okay, so we've got y equals 30 divided by x. And look at how our graph changed. Do you see it? So this is our parent function, the red line, And the blue line is our function that we just graphed, that we just solved for. And so they asked us to find what is y when x equaled what? What did we just solve for? What was x? Yeah, -6. And so here's x is equal to -6. And come right down here. And if I can get it right at 6, there we go. See? It's on the graph. So as long as you have the parent, or as long as you have the function, you can solve it graphically as well. But we had to be able to manipulate and find the equation of the line to be able to graph it to start with. And we just simply started with that one formula that I told you. Very important, very important, very important. Make sure that you have this formula. When you're looking at the whodunit, which is your project for this week, then you're going to be using this formula on every single assignment. Are there any questions? What type of function is it? Do you see it? Rational, exactly. Rational function. And rational just means ratio. And so this is very important. Any questions, guys? Nope. Okay. One final thing before we go, and I want to show you just navigating the Algebra 1 Google Classroom space. I don't know if you realize this. First of all, have y'all been getting a lot of emails, automated emails from Google Classroom today that was telling you that I was posting things? One of the things that I tried to do is I tried to turn that function, sorry, I tried to turn that function off. So that tells me that I read 2 different articles. One of them said that, you know, told me how to turn it off, and so I thought I did, but another article said that that is student driven, and so you can turn those notifications off, but I can't turn those notifications off for you. So that tells me that the second article I read was actually the correct one. But I did want to show you, yeah, you can see the stream can get very overwhelming. So one of the things that I've done is look at the classwork tab, because in the classwork tab, I can organize things. And so all you need to be focused with this week is going to be this 413 through 417 digital learning. All right, that's what the DL week 4 is for. So that's all you need to focus on this week. Since I did post it kind of late, because like I said in the beginning, I looked at 4.2 and decided you needed to pick up 4.1 before we did 4.2, then I've given you a little bit of extra time. But you can see just in this Zoom video, you know, really how simple these things are if we're able to break them apart and chunk them down into concise and digestible pieces of information. And then finally, I did want to show you the whodunit, which is your project for this week. So it's kind of a fun little game / project. And so you're going to be looking at, can y'all see it on your screen? Okay, so you're going to be looking at, basically it's a mathematical version of Clue using direct and inverse functions. And so you're going to answer these questions. You have all of these options, and in your notes, in your own notes, then you can copy this down or you can print it out if it helps, but you don't have to have a printer. And so you're going to go through each one of these clues, and there's 10 of them. And at the very end, then you have to submit who is the criminal, what was the location of the crime, and what was the type of injury based upon all of the possibilities right here. And you're going to use this y equals k divided by x to solve every single one of them. So it's kind of a fun thing. I hope it's a little bit lighter, and I hope you find it a little bit more enjoyable than just strictly bookwork. Yes? Better than just bookwork? Y'all know you can give me a thumbs up on Zoom. Okay, very good. Jonathan, what do you think?
Sounds good.
Sophie?
That's good.
Noah? Noah, you may need to unmute yourself. And then how do you submit it? The way that you submit it is going to be through this Google form. Make sure you put your name in, and then here is your sentence that you're going to tell me who the criminal was, what was the location of the crime, and what was the type of injury. So pretty simple stuff for you for this week. Just a few vocabulary lesson or vocabulary assignments. So I've done that through Google Forms as well. I've given you a list of all of your assignments. So there's only 5 things, and one of them being that whodunit. And that's pretty much all I have for you guys. Are there any questions?
Nope.
Nope. Nope.
All right. If everybody's good, feel free to email me, text me, call me, whatever you need. I'll be glad to help. All right.
All right.
All right, guys. Thank you so much for attending. I will see you online or next week.
Sounds good.
Bye, guys.